In the closing years of the 19th century, the world of science seemed orderly. Physicists believed they had a firm grasp on the fundamental laws of nature. The atom was thought to be the smallest, indivisible building block of reality. It was a solid, unchanging particle, the final stop in any quest to understand matter. But a strange discovery in a Paris laboratory was about to challenge everything. The story begins not with a grand experiment, but with an accidental observation. French physicist Henri Becquerel was studying a peculiar property of uranium salts. These salts were known to glow in the dark after being exposed to sunlight, a phenomenon called phosphorescence. Becquerel wondered if this glow was related to another recent discovery, X-rays. To test this, he placed uranium crystals on top of a photographic plate wrapped in thick black paper. The paper would block sunlight, but if the crystals emitted X-ray-like radiation, it would pass through and fog the plate. On a sunny day in February 1896, his experiment worked exactly as planned. But the Parisian sky had other ideas. Frustrated by the delay, Becquerel stored his unexposed photographic plates and uranium salts together in a dark drawer. A few days later, on a whim, he decided to develop the plates anyway. What he found instead was astonishing. A sharp, clear image of the uranium crystals was burned into the photographic emulsion. The uranium was emitting powerful, invisible rays all on its own, continuously and spontaneously. The discovery was profoundly puzzling. Where was this energy coming from? The phenomenon was a deep mystery, a loose thread in the otherwise tidy fabric of classical physics. The world was waiting for a brilliant mind to pick up that thread and follow it, no matter where it led. That mind belonged to a young Polish scientist in Paris named Marie Skłodowska. At the very time Becquerel was grappling with his mysterious rays, a new researcher was looking for a subject. Marie Skłodowska, who would later be known to the world as Marie Curie, had just completed her studies at the Sorbonne. Having earned degrees in both physics and mathematics, she was searching for a topic for her doctoral thesis. But Marie was drawn to the most obscure and unexplained of them all, the strange, persistent energy emanating from uranium. For Marie, the mystery was the attraction. She wasn't interested in grand, sweeping theories at first. Instead, she wanted to start with careful, systematic measurement. How strong were these rays? Did their intensity change over time? To begin her investigation, Marie needed a tool. Fortunately, her husband, Pierre Curie, was a brilliant physicist and inventor. Along with his brother Jacques, they had developed an extremely sensitive instrument, a piezoelectric electrometer. The invisible rays from uranium had the ability to ionize the air they passed through, making it electrically conductive. The electrometer could precisely measure that conductivity, providing a direct numerical value for the intensity of the radiation. She could now assign a number to the strength of the radiation from any given substance. This was the crucial first step. Her plan was simple but exhaustive. She would test every known chemical element to see if any others besides uranium emitted these rays. Then she would meticulously test a huge variety of rocks and minerals from a museum collection. A scientific investigation of historic proportions was about to begin, not with a flash of insight, but with the patient work of turning a dial and recording a number over and over again. For weeks, her laboratory notebook filled with entries. Gold showed nothing. Silver showed nothing. Then she tested a sample of thorium. The electrometer needle moved. The reading was clear and repeatable. Thorium was radioactive. She coined a new term for this phenomenon, radioactivity. Having established this fundamental rule, Marie turned her attention to natural ores. Most of the samples behaved exactly as she expected. But then she came across two minerals, pitchblende and chalcolite. The electrometer needle jumped. The measurements showed that these ores were far, far more radioactive than they should have been based on their uranium content alone. A sample of pitchblende, for instance, was 4 times more active than pure uranium itself. This was a shocking and inexplicable result. Marie checked her instruments and repeated the measurements. The results were always the same. There were only 2 possible explanations. Either her rule was wrong, or there was something else inside the pitchblende. There had to be a tiny amount of a new, unknown substance mixed in with the uranium, an element so powerfully radioactive that its presence completely overshadowed the uranium itself. This hypothesis was bold, and to prove it, she would have to find it. To begin this next phase of the investigation, Marie Curie needed a laboratory, more an abandoned shed than a proper lab. This humble space became the epicenter of a great discovery. They knew where to get it: the St. Joachimsthal mines in Bohemia. She had several tons shipped to their small Paris shed. It was a mountain of waste. To the Curies, it was a treasure trove. The work became industrial labor. For hours, Marie stood over steaming cauldrons. She stirred with a heavy iron rod as tall as she was. It was a repetitive, grueling cycle of heavy lifting, crushing, boiling, stirring, day after day, week after week. The first step was to add hydrogen sulfide to the solution. This created a dark, heavy sludge that settled at the bottom of the vats. This separated the mixture into a solid precipitate and the remaining liquid solution. The result was clear. The solid sulfide precipitate was intensely radioactive. The liquid had lost most of its activity. This was a major breakthrough. The unknown element behaved chemically like bismuth. They could discard the huge volume of liquid and focus on the much smaller solid precipitate. The haystack was already getting smaller. By July of 1898, after months of relentless labor, Marie and Pierre Curie were confident. They had successfully concentrated a substance whose radioactivity was about 400 times greater than that of uranium. Marie chose to name it polonium in honor of her native land, Poland. It was a way of putting the name of her oppressed country on the scientific map. After the polonium was removed, the remaining material from the pitchblende was still highly radioactive. Instead, it followed the chemical behavior of barium, an alkaline earth metal. They repeated this cycle hundreds, then thousands. The work consumed their lives for the next 4 years. Eventually, they produced a tiny amount of a whitish salt that was almost 1,000,000 times more radioactive than uranium. It glowed in the dark with a steady, ethereal blue light. Marie Curie described in her notes how they would often return to their cold, dark shed at night simply to look at their creation. They proposed the name radium, from the Latin word radius, meaning ray, in honor of its most spectacular property, its intense radioactivity. When this pure sample was put into the spectroscope, the result was undeniable. The phantom had been captured. For this work, Marie Curie, Pierre Curie, and Henri Becquerel received the Nobel Prize in Physics in 1903. But Marie Curie understood the implications were far deeper. The intensity of the rays depended only on the amount of uranium or thorium present. The energy was not coming from bonds between atoms, but from within the atom itself. Radioactivity was an atomic property. This was a radical and subversive idea. The old model of the atom could not account for it. This led to the revolutionary concept of radioactive decay, the idea that a radioactive atom is unstable and turning into a completely different element. This process, known as transmutation, was the stuff of alchemy. Yet here was nature, doing it all on its own. This tiny sliver of lost mass is converted directly into the energy of the emitted radiation. This is why radium could produce so much heat and light. Physicists realized they could use them as a new kind of microscope. That experiment showed the atom's positive charge and most mass sit in a tiny dense nucleus. She unlocked the door to the atomic nucleus, and in doing so, she launched the new science of nuclear physics. Today, the dangers of radioactive materials are well known and strictly regulated. But at the turn of the 20th century, none of these dangers were understood. She would keep a glowing vial of radium salt by her bedside as a nightlight. When they pass through living tissue, they act like microscopic bullets, tearing through cells and shattering the delicate structure of DNA molecules. In 1934, at 66, Marie Curie died from aplastic anemia. Her doctors concluded that long-term radiation accumulation caused her fatal illness. To this day, Marie Curie's laboratory notebooks from the 1890s are still dangerously radioactive. They are stored in lead-lined boxes. Her furniture, her cookbooks, and other personal belongings also remain radioactive. The story of the Curies is therefore a dual one. It is a story of brilliant scientific discovery, but it is also a cautionary tale about the unknown dangers that can accompany new knowledge. Her work unlocked the door to the atomic nucleus and laid the foundation for modern nuclear physics. The unchangeable clock of radioactive decay gave us radiometric dating. The destructive power of radiation was turned into a powerful weapon against cancer. Our story began with a simple, unexplained shadow on a photographic plate. Marie Curie's investigation did more than just discover new elements. It gave humanity a new universe to explore, the one hidden inside the heart of the atom.